Hi students, I am Prashant B. Chandran, Assistant Professor Automobile Engineering Department, SN80 Adur. Okay, we have already discussed about heat exchangers and the analysis of heat exchangers, that is LMTD method and NTA method. Now I am teaching you a problem on LMTD method. Okay, let's start the problem. It is, in a food processing unit, a brine solution is heated from minus 15 degrees centigrade to minus 7 degrees centigrade in a parallel flow heat exchanger by water, entering at 35 degrees centigrade and leaving at 20 degrees centigrade at the rate of 12 kilogram per minute. Okay, that is, there is a food processing unit in which a brine solution is heated from minus 15 degrees centigrade to minus 7 degrees centigrade. If a fluid is heated from a lower temperature to a higher temperature, means that fluid can be considered as the cold fluid. That is, here the brine solution is heated from minus 15 to minus 7 degrees centigrade. So we can consider this brine solution as the cold fluid. Okay, and it is given that it is a parallel flow heat exchanger, and this brine solution is heated by water. It is entering at 35 degrees centigrade and leaving at 20 degrees centigrade. That is, the temperature of water is going on decreasing from inlet to outlet. That is, this is the hot fluid. Okay, don't make any mistake in this. Okay, it is hot fluid is losing the temperature, and the cold fluid is gaining the temperature. Okay, leaving at 20 degrees centigrade at the rate of 12 kilogram per minute. That is, the mass flow rate of the hot fluid, that is mass flow rate of water, is given as 12 kilogram per minute. But we have to convert that into second. Okay, then determine the heat exchanger area for an we have to find out the heat exchanger area, and it is given that the overall heat transfer coefficient is 850 watt per meter square Kelvin, and the CP, that is specific heat at constant pressure for water, as 4.187 kilojoule per kilogram Kelvin. Okay, this is the problem. Once again, it is a problem from LMTD method. It is given that it is brine solution is heated from minus 15 to minus 7 degree centigrade, means the brine solution is the cold fluid, and it is a parallel flow heat exchanger, and water is cooled from 35 degree to 20 degree, means water is the hot fluid, and the mass flow rate of water is given at 12 kilogram per minute. We have to find out the heat exchanger area, and the heat transfer coefficient is given as 850 watt per meter square Kelvin, and the CP for water is given as 4.187 kilojoule per kilogram Kelvin. Okay, first of all, we have to write the hot and the cold fluid separately. Okay, we are writing the cold fluid and hot fluid separately. That is, we can recognize the cold fluid, that is, temperature is increased in case of a cold fluid. Okay, that is, here the brine solution, if you consider brine solution, the temperature is increased, and if you consider the water, the temperature is decreased. That is, brine solution is the cold fluid, and water is the hot fluid. That we can write the temperatures, that is, inlet temperature of brine solution is minus T1 is equal to minus 15 degrees centigrade, and outlet temperature of brine solution small t2 is minus 7 degrees centigrade, and considering the hot fluid, the inlet temperature is T1, capital T1 is equal to 35 degrees centigrade, and outlet temperature of hot fluid, capital T2, is 20 degrees centigrade. Then it is, in case of hot fluid, it's CPH, that is specific heat at constant pressure for hot fluid, is given as 4.187 kilojoule per kilogram Kelvin, and the mass flow rate of the hot fluid, that is water, that is m dot h, is given as 12 kilogram per minute. M dot h is equal to 12 kilogram per minute. We have to convert it into kilogram per second. That is 12 by 60. 12 divided by 60 kilogram per second. Okay, kilogram per second. And the overall heat transfer coefficient U is given as 850 watt per meter square Kelvin. Okay. Then to find the question, it is said that we have to find out the heat exchanger area A. Heat exchanger area capital A. We have to find it out. Okay. Then our solution. First of all, we have to draw a temperature distribution diagram. Temperature distribution diagram for a parallel flow heat exchanger. For a parallel flow heat exchanger. Okay. This is the first step. Without this temperature distribution diagram, we can do nothing. Okay. That is, first I am drawing the hot fluid line. That is, here the hot fluid is water. Water is the hot fluid. And its inlet temperature is capital T1 is 35 degrees centigrade, and the leaving temperature or outlet temperature of hot fluid is 20 degrees centigrade. Okay. Then I am drawing the cold fluid line. That is, cold fluid is brine solution. Brine solution is the cold fluid, and the inlet temperature of the brine solution is small t1 is equal to minus 15 degrees centigrade, and the outlet temperature of the cold fluid, that is small t2, is equal to minus 7 degrees centigrade. Okay, and this is actually theta 1, that is capital T1 minus small t1, that is temperature difference at the left side of the heat exchanger is theta 1, and the temperature difference at the right side of the heat exchanger is theta 2, that is capital T2 minus small t2. Then we have to find out the value for LMTD, that is logarithmic mean temperature difference, or delta T LM. That is LMTD is given as, the equation is capital T1 minus small t1 minus of capital T2 minus small t2, the whole divided by ln of capital T1 minus small t1 divided by capital T2 minus small t2. The next step is giving the values for these T1, T2, etc. This capital T1 is 35 degree minus small t1 is minus 15 degrees centigrade. You have to place a bracket, otherwise a mistake will be coming there. Okay, minus of capital T2 minus small t2. Capital T2 value is 20 degrees centigrade minus of minus 7 degrees centigrade. Okay, the whole divided by ln of capital T1 minus small t1, that is 35 minus of minus 15 degrees centigrade. 35 minus of minus 15 degree, the whole divided by 20 minus of minus 7. Okay. While calculating this in your calculator, you get the value of LMTD is equal to 37.33 degrees centigrade, which is also equal to 37.33 Kelvin. Okay, both are correct. You can write it in degrees centigrade or Kelvin, whatever it may be. The answer is correct. Okay, plus considering the difference. Okay, then you have to find out the heat transfer for either the hot fluid or the cold fluid. But here, if we consider the hot fluid, its mass, specific heat and temperature difference are given. Therefore, we can directly find out the heat transfer of the hot fluid, that is QH is equal to m dot H into CPH into capital T1 minus capital T2, that is mass of the hot fluid into specific heat of the hot fluid into temperature difference. Mass of hot fluid is, we have already found out the value as 12 divided by 60 into 4.187 into temperature difference, that is 35 minus 20. We get the value as 12.561 kilowatt, because 4.187, that is the value of CPH, is in kilowatt. Therefore, we get the answer in kilowatt. Okay, value of CPH is in kilojoule per kilogram Kelvin. You have to convert that into that kilowatt into watts. That is, we get 12561 watts. This is the value for heat transfer of the hot fluid. And also there is another equation for heat transfer, that is Q is equal to UA LMTD. Q is equal to UA LMTD, where Q is the heat transfer, U is the overall heat transfer coefficient, A is the area of cross section of the heat exchanger, and LMTD is the logarithmic mean temperature difference. Therefore, U is equal to Q divided by U into LMTD. Sorry, A is equal to area is equal to Q divided by U into LMTD. That is, the value of Q is 12561 divided by U value is 850 into LMTD. We have already found out the value of 37.33. That is, we get the value for area as 0.396 meter square. This is the value for area of heat exchanger. Okay. Thank you for watching this video. Have a nice day.